gonna restart the recorder because I don't know what changing. Oh, it doesn't like it. It looks okay now. Okay. All right. Move it back up. So is that okay? Yep. Okay. So let's go ahead and just finish this up because this way you can get started with your homework assignment. Let me check. Recording is on. Good. Okay. So we have params .c and xyz.uppercase s. So these are the two files. I did not save the file on the other side, but that's okay because that's not what I want you guys to do. I do not want you to refer to each individual item by the number, okay? Because even though we can count the numbers, the spreadsheet is still here, so we can just look at the spreadsheet and see how the numbers are assigned. Not this one, but this one here. Okay, so we can still see the numbers. We can always refer to the pointer as 256 bytes below where EBP points to, okay? But referring to 256, 260, the first argument is at 8 bytes above where EBP points to, it's not a good way to refer to individual items. So what I want you guys to do is to use symbolic names. And this is what I usually do. It doesn't mean that you have to do it, but I personally find this to be useful, is to assign symbolic names. So what I do is I say EBP or old EBP equals to 0 because it is 0 bytes away from where EBP points to. Is that okay? Because when you look at the picture, when you look at the spreadsheet, you can see that EBP points to these quote-unquote 4 mysteria bytes, but these 4 mysteria bytes is the actual value of EBP before we change it. So that's why old EBP is 0 because the offset from where EBP points to is 0. So we can do the same thing with all of the other items. Okay, getting back to the source code here. The next one up is always the return address. So but instead of saying the return address is 4, I just refer to it as old EBP plus 4 because now it is just relative to the previous item. The next one up is which one? Can you guys remember? Well, it's on the map itself. So what is the next one? It's the first parameter. The first parameter has a name of destination. So I'm going to use the same name as my symbolic name here. So destination is return address plus 4 because the return address itself is using up 4 bytes. So the starting point of the first argument is 4 bytes above where the return address is. Is that okay? Now remember, destination, DEST, is not the actual argument. It is the number of bytes between where EBP points to the base of that argument. Okay, it's a displacement. It is not the actual location. The next one up is source. So source is destination plus 4. And the last one is n, which is source plus 4. So these are all displacements. On the other side, we have our local variables. The first local variable that we need to allocate is going to be buffer. So buffer is old EBP, but this time minus 256, because when you look at the picture, okay, not this one, but when you look at the picture, this is where EBP points to, which is its own old saved value. This is where buffer is, or the beginning of buffer. This is 256 bytes below where EBP points to. And then PTR, which is my local variable pointer, is going to be 4 bytes below that. So PTR is going to be buffer minus 4. Is that okay? Now, as a personal thing, I like it. You may or may not, want to follow the same thing. Is I always have one thing called last local variable. In this case, it is my PTR. So now I'm going to use that to adjust the stack pointer. So I would say add long is add because it is a negative number. So when you add a negative number to the stack pointer, you are allocating additional space. So we are adding $last local variable to the stack pointer. This is how I usually allocate for the local variables. Okay, so this way, I can change by changing how these labels are defined. I can define additional local variables. I can adjust the space, but the rest of the code can remain exactly the same because they all refer to the names, the symbolic names. Are there any questions about this code at this point? No questions? Okay, so without any questions, we are going to implement this program line by line. So to do this, I'm going to do it line by line. So I'm going to put the C code here first, and then we'll use the assembly code to do this. This one we have figured out already. So we can say move long EBP, to EAX, so we can do the calculations in EAX instead of EBP, because you don't want to change EBP during the execution of a subroutine. And then we have to compute the address of buffer, so that is just adding the displacement of buffer to EAX. So at this point, EAX becomes the address of buffer. We want to store it into our local variable pointer. And because we can make use of the base addressing mode, we can just say copy EAX to PTR in parentheses EBP. This is the base addressing mode. I haven't really done anything differently compared to what we talked about in the lecture. The only thing I have changed is to use the symbolic name instead of the actual number of -260. But the program is more readable this way, because you can actually see that we are calculating the address of buffer and storing that into the local variable pointer. Are we doing okay so far with this code? Okay. All right. Next one is the while n. Okay. So while n as the beginning of a loop. So we want to handle this structure as a whole. So that means, just like any while loop, it has a while begin, it has a while end, and right before the end, we want an unconditional branch back to the beginning. This is the structure of a loop. And then we have to specify the condition so that we can specify when are we exiting the loop to branch directly to while end. Well, in this case, we are only looking at not local variable, but the parameter n. So how do we test whether parameter n is 0 or not? What do we do? With one single instruction, how do we compare parameter n with 0? Sorry? Compare, okay. CMP long, okay, very good. Now this time it is actually important. What are we comparing? With what?
0.
We're comparing 0, so the constant 0 has to go first because this is a immediate operand. You cannot specify the immediate operand as the second operand. What is the second operand? What are we comparing to 0? Well, we are comparing n, but remember what n as a label is. N as a label is not actually the memory location of the parameter. We have to use the parentheses EBP because n is only specifying the offset or the number of bytes between where EBP points to the parameter itself. So we have to use in parentheses EBP to specify this is our based addressing mode. Are we still doing okay so far with this code here? We're comparing parameter n to 0, which is exactly what we are doing in C. What do we do next based on the result of the comparison?
Jump 0 to n1.
Yep.
Or 1.
Yep. Jump 0 to while n, because when n becomes 0, we want to branch out, which is the meaning of while n. Because while n is basically saying as long as n is non-zero, stay in the loop. Well, let's see. If n is non-zero, stay in the loop. If you flip to look at the exit condition, it means when n is 0, get out of the loop, which is what these two instructions, the compare long and the JZ instructions, are doing. Okay, what do we do in the loop the first thing? We decrement n. How do we subtract 1 from n?
Subtract 1.
Subtract long, okay.
Constant one.
$1 from,
And we can see C.
exactly, because we are actually subtracting 1 from the parameter itself. But we're still doing okay so far with this code. Okay. And then what do we do next? Well, what we're going to do next is store the least significant A bit of n into where PTR points to, and then increase the pointer by 1, increment the pointer by 1. Okay, you guys can help me out, and what are we going to do here?
Move byte.
Okay. Okay, this is what we want to do, but whether we can do it or not is a whole different thing. So we want to move byte and EBP to where?
We need to make another register that points to this because we can't have 2 memory operands.
We have to separate this line into multiple instructions. Okay. Well, you can always put it into CL or something like that first, and then copy from CL to something else. Okay, so we can do that. So we'll copy this to %CL, which is the low register or the least significant A bit of ECX. Okay, we'll just keep it there for a while. And then we want to compute, where am I going to store this to? Well, the C code says it is not being stored to PTR. It's being stored to where PTR points to. But PTR by itself is a local variable. It is sitting on the stack, which means I have to put it into a register first, because you can only dereference a register. You cannot dereference a memory location in assembly code. Okay. So what we need to do now is to say move long, okay, move long, PTR EBP, because this is the pointer itself. We are copying the pointer, which is the address of the byte that we want to store to, into a register. We have already used, well, EAX is not really useful at this point. We can just use it. So we'll keep using EAX. In your code, in your program, you can freely use EAX, ECX, and EDX in your assembly code. But when you call another subroutine, you cannot count on those registers retaining its value. Okay? It is the caller's responsibility to save the values of EAX, ECX, and EDX if those registers are in use by you. Okay? EBX and EBP are preserved by the callee, the subroutine being called. So you can count on those registers being preserved. Is that okay? Sort of? Okay. Okay, so I'm just going to copy this into EAX because EAX is just a useful register in general. So now EAX has the address of where I want to store the byte. I can now actually store the byte, which is a move byte, CL, which contains the byte, the source, the byte that I'm trying to transfer, to copy, to indirect EAX, because EAX at this point has the address of the destination. Is that okay? Next instruction is to do the post increment. And the post increment is fairly easy to do. Just add long $1 to PTR EBP. That would do the post increment of pointer. So together, these 5 instructions is doing that one single line in C code. So let me just point out in here, these 5 instructions in assembly is doing this one single line of instruction or statement in C. All right, so this is done. We have the unconditional branch already. Okay, so here comes the other fun part, which is from assembly code, how do I call a subroutine that is in the C library? Well, guess what? It follows exactly the same rules that we have been talking about. That's the whole point. Because if everybody follows the same rules, they can all operate together, they can interoperate. So now we can say, okay, we want to call string and copy, which is an actual C function. What do we do? Well, we know that we have to call at some point, okay? So call is easy, call string and copy. But before we call, don't we have something to do?
have to put,
the arguments.
yeah.
Yeah, we have to push the arguments. But in what order?
Size of buffer destination.
Yep. And since we have a cisp architecture, we can push the constant. What is the size of buffer? 256 bytes. So we push 256 as a long on the stack first. And then what is the next one? We're pushing buffer. But now you have to be careful.
Buffer
Because
is
what
an
is
address.
buffer? Buffer is an array. And with arrays in C and C++, you can only pass by address. You cannot pass by value. So even though it seems like we want to do this, that's not what you want to do. Because what this is going to do is to push the first 4 bytes of the array of 256 bytes on the stack, which is not what you want to do. Because you want to push the address of the array on the stack, not the content, not the first 4 bytes of the content. Okay, so if this is not working, what are we going to do? Oh, I know. The address of operator, like that. Well, that won't work either, because this does not work in assembly code. There's no such thing in assembly code. Well, what do we do? Well, okay, let me show you the long way of doing this, okay, which is not really the bad way. It's just longer in terms of number of instructions. So what we can do is, well, okay, we can copy EBP to EAX again. And then in EAX, we can compute the address of buffer. Haven't we done this before? So what do we do next? Same thing as last time? Not subtract, because buffer is already a negative number. We have, it's already on the projector. Computing the address of buffer is already on the projector. It's just a few lines down from the top. This part here. Okay, so we just add $buffer to EAX. Because the first thing I did was to copy EBP to EAX. So now they both point to the same place. But we already know that buffer is 256 bytes below where EBP points to. So if I do the same adjustment to EAX, then EAX is now pointing to the base of the entire array. And then what do we do is we want this to be my argument. So how do you pass an argument? Push it on the stack. Just like that. Any questions about this step? These 3 instructions.
So if you hadn't have used EAX in the while loop, you wouldn't have had to do any of that code.
If I have been using EAX as, oh, okay. If I'm not using EAX, yeah, you're correct. But yeah, because I'm not calling any subroutine in the loop, so I can count on EAX still having the same value. Yep, correct. Yep.
Is the reason you cannot pass the array by the values because it doesn't fit in the register?
No, because in C and C++, there's no such feature. The programming language itself does not support passing an array by value.
Okay.
You can pass anything by value, even structures, but arrays cannot be passed by value.
In the parameter, once you pass in the array, does it matter what number you put inside of the array brackets?
I do not believe you can specify the number in square brackets as a parameter.
Yeah, there is no, but I see people putting the number in there, and I'm curious, does it have any effect on the parameter?
Well, we can test that next. Okay, let's finish this one first.
Yeah.
Yep. Okay, so are we done with parameters? We are trying to implement the string and copy call. Are we done with parameters? We have one more, which is destination. Now here's the trick, okay? Because from the perspective of the C code, it's kind of the same thing, okay? The way we pass destination and the way we pass buffer is still just referring to the name of the parameter or the local variable. But in assembly, it's an entirely different thing. Because what is destination? What is DEST? Is it an array that actually has a whole bunch of bytes allocated to it? Or is it just a pointer? It's just a pointer, okay? Because the way destination is declared is clearly that it is just a pointer. The way we declare buffer, on the other hand, is it is an array with bytes allocated. So you have to make sure that you differentiate between these two cases, because one actually has a bunch of bytes allocated, the other one does not. The other one is nothing but just a pointer. But from the perspective of assembly code, that makes our job easier, because what we can do is just to say, oh, we just want to copy whatever is on the stack as the destination, just copy it one more time on the stack at a different place. And you can do this. This is a cisp instruction, which is actually combining a whole bunch of stuff, into one single instruction. Because what you're doing is you're retrieving the 4 bytes that are, this many bytes away from where EBB points to. Retrieve those 4 bytes and then push those 4 bytes on the stack again. Is that okay? Yes? No questions? Well, focus on one thing at a time. Focus not on the push out instruction, just focus on the operand. Okay? The operand is a base addressing mode, which is basically saying we want to retrieve something. That something is close to where EBB points to, but not quite exactly the same, because it is DEST, which is a symbolic name defined earlier, is that many bytes away from where EBB points to. Go to that location, retrieve 4 bytes, and then push those 4 bytes on the stack. Yep.
How to make it a lot more than the 4 bytes? Is it possible to push like 400 bytes or something?
If you want to push 400 bytes, you are better off by allocating the bytes first and then call memcopy to copy those 400 bytes. Assuming you're copying 400 bytes from another 400 bytes.
Yeah.
Yeah, you can do that.
Oh,
But
so
it's
another subroutine is easier and faster.
Yeah, memcopy. Yep. Okay, now we have all 3 parameters pushed on the stack. What do we do after we have everything pushed? Call. Okay, it's just a call instruction. Now, string n copy does return a result. Am I making use of that return value in the C code? String n copy returns, a pointer. It basically returns the first parameter. But am I doing anything with the return value of string n copy? So that means when this call returns, EAX has a particular value, but I'm not using it. It's not useful to me, so I'm going to ignore that. At this point, it is important for me to emphasize that I need to do this to the stack pointer. What am I doing to the stack pointer? Why am I adding 12 to the stack pointer?
Because you just added.
I got one push long, another push long, another push long here. Those are the parameters to the callee. Now that I have returned from the subroutine, are those parameters useful to me as the caller?
No.
They're not useful. So if they're not useful to me as a caller, I'm readjusting the stack pointer. If I add 12 to the stack pointer, am I growing the stack? Am I using more space on the stack? Or am I using less space on the stack? Am I deallocating or allocating? I'm deallocating. In other words, the 12 bytes that I push on the stack for the parameters, they are useless now. To the caller, the job is done. So I'm deallocating those 12 bytes so that I can reuse those 12 bytes if I need to for other things. Is that making any sense? Sort of? How many people took cisp310 from me? That has to be a long time ago. Do you guys remember that we have to deallocate things on the stack? That's what this is. Okay? In other words, this has been along, since cisp300. It's just that in that class, we use a spreadsheet to look at the thing, and now we look at those things from the perspective of assembly instructions. Okay? So we are done with the string end copy. We have a return 0 at this point. Return 0 in C has two things to do in assembly code. Because return 0 specifies the return value on one, that's the first thing it does. The second thing it does is the actual termination of the subroutine. But you cannot do both in one single instruction in assembly code because you have to specify the return value, which is a scalar in this case, in which register?
EAX.
EAX. So how do we specify a return value of 0?
Move along. 0 to EAX.
Yep, that specifies a return value of 0. But the actual termination of the execution is down to these three instructions. It's not a single return instruction because we still have to clean up the stack. Because at the point of this instruction, let me turn on the line number so it's easier to point to which line. Because by the time we are done with line 44, the stack is still not done yet. Because at that time, on line 44, let me see if I can do this. So I'm going to slide this one to this side here so we can look at the spreadsheet at the same time. So by the time we are on line 44, when line 44 is done, the stack pointer is still here. In other words, we still have all kinds of stuff on the stack. The stack pointer is pointing to the last local variable that we have allocated. So what if I'm going to run the return statement, return instruction right now? It's going to use buffer. It's going to use pointer as my local variable as the place to go back to. It's not going to work. So what I need to do is to clean up the stack. The way I clean up the stack is to copy. So if you look at the instructions here, the first thing we do is on line 47. Line 47 is copying the frame pointer to the stack pointer. The frame pointer is pointing to the old EBP value, okay? And the stack pointer is pointing over here. So what I'm copying is from here to here, which means after line 47, both the stack pointer and the frame pointer will be pointing to the old value of EBP. Is that okay? So that means line 47 is responsible to free up all the space that I have allocated for local variables, but not old EBP itself. Old EBP would still be on the stack by the time I'm done with line 47. The job of line 48 is to restore the value of old EBP into EBP itself. Is that okay? So once we are done with line 48, EBP will be pointing somewhere else. I have no idea where it's pointing to, but it's not my job to know. But the stack pointer will now be pointing to the return address. So I'm all set up for the return instruction right after that. So that's how a subroutine is supposed to work. Are there any questions at this point about all of this code and the picture of what we call a call frame looks like? This is called a call frame because this is the construct, this is the structure of the stack related to a single call or invocation of a subroutine. Yep.
Is it necessary to have move L and pop L, line 47, 48 as different lines? Couldn't you just basically move 4 more bytes up?
No, you cannot because we actually want the old value of EBP back to the register. In other words, we actually want these 4 bytes to go back into EBP before the return.
Okay.
So that's why that pop L has to be there. We cannot just adjust the stack pointer past that point. Okay. Any other questions? Yep.
Yeah, quick question. Just to verify, when you move along EBP to ESP, you move the address of those question marks or the value?
No. I am just adjusting. So after this instruction, after line 47, then I will have this situation. So I have EBP and ESP pointing to the same location. I'm moving the pointer. I'm changing the value of the register so that both registers will point to the same location. Yep.
And the second question is, pop long EBP.
Mm-hmm.
Oh.
So after the pop long EBP, EBP will end up pointing to somewhere else, but then the stack pointer will point back to the return address because every pop instruction is moving the stack pointer up because it's also deallocating.
Okay. So it moves EDP, whatever it is, but what's important is ESP is going to move up once.
Right. Yep. Now this is also but once we understand the basic structure of the entry code, exit code of a subroutine, and also a call frame, now we actually understand why how BT or backtrace works. Do you guys remember backtrace? Sort of.
Reverse engineering.
For multiple purposes. If you have main calling A, calling B, calling C, calling D, if you put a breakpoint in D, you can use BT and it will show you that main calls A, calls B, calls C, calls, and now eventually you're in D. How does BT work? How does it know that you are being called from which other subroutine and that in return is being called by which other subroutine? How does it know that? It has to do with this picture. Okay, so what I'm going to do is to show you a picture. It's harder to draw it in a spreadsheet, but it's easy to draw it on the whiteboard. Okay. And finally, here. Some of you might want to take a picture of this because this can be helpful. This is one of those things where you say, why are we learning Latin in an English class? And it is actually useful. This is one thing you can take away and go like, oh, so that might be useful. A call frame in general has two things that has to be there. The parameters may not be there. The local variables may not be there. But two things has to be there. The return address and the saved EBP. Okay, return address and old EBP. Okay? And once the call frame is set up, what is EBP itself pointing to? It's always pointing to old EBP. Okay? So you have the actual registered EBP pointing to the saved value of itself before the invocation of this particular subroutine, right? So what if you are to call another subroutine using the same standard? Okay, you have another call frame, right? It might have parameters, it might have local variables, but two things it must have are the return address and what else?
Old EBP.
And where EBP came from.
And the saved EBP. Okay, so old EBP is here. But who is the old EBP in this case?
The value of the address.
Exactly. And what is EBP going to point to right now at this point? The second, the lower EBP, right? So what happens when you call again from here? Same thing. Another call frame is allocated on the stack, and two things you can count on in a call frame are the return address and the saved EBP. Return address, old EBP. But where is this old EBP actually pointing to? The previous old EBP. But what about the actual registered EBP? What does it point to now? The current old EBP. Okay, very good. Okay. So when you look at this picture, what does it remind you of? Especially for those of you who have taken 430. CISP 430. It looks like a irregularly shaped linked list. Okay? Now, it is irregularly shaped because I have no idea how many bytes are here, how many bytes are here. How many bytes are here or here, here or here. Because that is determined by the actual subroutine. It's determined by how many parameters it has, what kind of parameters, and whether it has local variables or not.
So it's super flexible. So,
yeah. But I can look at, once I have EBP, I can do backtrace.
You can.
Because backtrace is basically using EBP to get to this frame here. But once I get to this frame, the first thing I look at is, well, there's also the program counter, right? The program counter is always available. By looking at the program counter, I know which subroutine I'm in at this point. Is that making any sense? Once you know which subroutine you're in, the compiler, using the debug information, it can figure out what kind of parameters you have and what kind of local variables you have. That's why it can show you all your local variable and parameters by using the EBP and also the program counter. But what about the earlier frames? How does it get to the earlier frame? It's using this guy to go back to the previous frame. But in the previous frame, how does it know which subroutine is creating this frame here?
Right, the return address?
The return address, exactly. Because the return address has an address of where you came from, the caller of this subroutine. So by using the return address, it knows the structure of this particular call frame. And that's why BT works, because BT can now display the parameters of the earlier invocation or the previous invocation. But by following this ODBP, it can go back again. By using the return address, it can now interpret the other frame as well. So that's how BT works. Backtrace makes use of the frame pointer. In addition to that, the program counter. But once it knows the program counter, the current program counter, and EBP, it can rely on those two saved values on the stack to go all the way back to main. Is that kind of helping you understand, how BT or backtrace works?
Yeah.
But what happens when you mess up one of these two things?
You laugh.
Bad things will happen, right? Now, if you trash return address and you trash it with all zeros, that's one of the easier problems to solve, because your program will simply crash with a segmentation fault, and when you debug it, when you use GDB, it will tell you that it is trying to execute at location 0. Because what happens is the return instruction at the end of a subroutine is trying to return to location 0 to continue execution. So that's a relatively easy problem to solve, because you know that the return address of the current invocation is messed up. So you know which subroutine you should look into, right? And you have a fairly good idea of what value you overwrote on the stack, which is all zeros. Easy problem. What if you mess up the old EBP? What if this location, I'm going to use red here, and say, what if this location is messed up? It's not going to crash when you return. It will crash after you return, because the problem is when the previous invocation, when you restore this old EBP into actual EBP itself, you're already back to the caller. So the caller is going to cause the crash. Is that making any sense? Mm-hmm. But that's not the worst either. The worst thing that can happen is, what if you have old EBP only adjusted by a little bit?
It's gonna work.
So you have old EBP and you say +2. What's going to happen? This invocation is going to exit just fine. Return has no problem returning. It will restore old EBP +2 to EBP. So when you return to the previous invocation, EBP is supposed to point here, but not anymore. EBP is now pointing to 2 bytes above where it is supposed to. What is the effect of that? We have seen it already. Remember that program thing that access local variables but off by a little bit? That's what's going to happen. Now, what if this invocation of a subroutine is not adjusting its own ODBP, instead it's adjusting somebody else's ODBP? So by the time the symptom happens, you are light years away from where the problem was. So what do you do? What do you do when you see odd symptoms? Like, you main calls F, but it returns to G, which was never called from anywhere in the program. Or you try to access your local variables. They all seem to be off, and it's just like, oh, it's one variable off by location, what do? What do you suspect? You have something that trashed the stack. But what is the most likely cause of something trashing the stack? Oh, let's go back to the C code, okay? Something like that. Pointers. Okay? Now this is a unique problem, okay? If any one of you is saying, I will never ever program in C or C++ because I'm a Java programmer, I'm a Python programmer, then you don't have to learn any of this stuff because this will never bother you at all. But if you program in C or C++ and you use pointers, especially when you use calculations and use pointers like this, at some point it's going to happen, okay? And you say, well, but I don't use pointers. I know pointers are dangerous. I never use pointers. Instead, I use arrays, okay? So let me just switch gear here. Okay. So you say, I don't use pointers. I use something that is a lot more civilized, like buffer bracket I equals something. That's not going to save you.
I can overflow. I can overflow.
I can overflow because there's no bound checking in C or C++. Okay? And you would look at this and say, but it does have all the information because buffer is a local variable. It is an array declared in this function. The compiler should know how big the buffer is. Yes, the compiler does know, but it does not generate the code to do the boundary checking. So you can say buffer bracket 600 and something and try to assign something to it, it will let you go. Not a problem.
But
Yep.
if it overflows past the allocated memory for the program, it will crash.
Yes, if it is like way, way, way over there, which is beyond the limit of the stack, yes, it will crash. But what if it is not? What if you do something like this? Then you trash that location that that does not belong to you. But the way you trash it is not you're putting all zeros into it, you're not putting all gibberish into it. You're only adjusting it by 2. What if that location, what if buffer bracket 600 turns out to be a return address? What if it turns out to be ODBP? Now you have really odd symptoms. That is what happens. This is how things happen in C and C++. Is when you trash important stuff on the stack, then your bad things will happen. But depending on what you trash, the symptom can be different. Yep, go ahead.
This is a odd question. 430, the data structure. Is there any way to learn it without C++, or do you always have pointers to do the linked lists and stuff?
I will leave it to someone who has taken 430 to
Iraj
see.
teaches it just in C++.
Okay.
No, but besides C++, is there any other way of...
Well, even in C++, there are ways to do things without using pointers all completely. The question is, does the professor teach it in that way? Does Iraj teach it using pointers or not?
Yeah, pointers and just C++.
Yep. So you do have to use pointers.
What's the alternative to that? That's the question.
The alternative of not using pointers?
Yes.
You can use references.
Reference?
Yeah, you can have a member property that is actually a reference, not a pointer. Now the difference seems really minor, but the use of a reference means you cannot do calculations based on it, and therefore you avoid all of these problems.
Or features. They can be problems or features.
They can be, exactly, yep.
So you can create a linked list using references?
With only references but not pointers. Yep. Okay, any other questions? Well, even for those of you who say, well, I am a good C++ programmer, so I only make use of save features. Well, that's not going to save you when you become employed. Why?
Because someone else is going to write a code that you're going to use.
And you are going to maintain it. When someone files a bug report and say this program crashes with a segmentation fault, You are going to have to fix that program. So even if you personally do not do anything dangerous like that, it doesn't mean that you do not have to know about it or to fix problems like that. Because somebody else is going to write code like that, and it will be your job to fix it. So if you want to if there's anything that I think is really important out of this class, we are now getting into it. The last 2 weeks of the entire semester, okay? But everything else built up to this point. We cannot talk about this without the stuff that we talked about earlier. Okay? So your homework assignment is due on next Thursday, but I would suggest you guys to start really early to work on your homework assignment so that on Thursday you can bring your questions and I can try my best to answer those questions. Okay? Well, that's going to be, this is the end of the recorded lecture part. You guys can stay here and do the homework. I would say, use the next half hour or so to get started. Okay, just because, this is all fresh, you can do your own experiment, find out stuff, because this stuff is not easy to remember.